voir si je te coupe. Je l'ai pas, je me suis pas branché, je l'ai pas mis. Mais l'autre, pour voir, je vais essayer de faire dans l'audio. Ouais. D'accord. Ok, là, je pense un participant. Activer, je peux faire ça encore. Ouais, je peux l'activer, après je vais faire. Tous qui s'inscrivent. JB. C'était 2 minutes, 5 minutes.
Hello, everyone. Did the lecture start?
Not yet.
Not yet.
Okay, thanks.
Okay, Christina. So we are all ready for the last lecture of this school before next week, before the workshop next week. So please.
Hello, everyone. Thank you for arriving for the final lecture of my series, and thank you so much for the opportunity to speak. I'm going to start this lecture at a lower level where we assume we have Riemannian manifolds again, and I will discuss an estimate for estimating the distance between two intrinsic flat, the intrinsic flat distance between two Riemannian manifolds. That's joint work with Sajjad Lakhsian. And then I'm going to talk about joint work with Raquel Perales and Brian Allen, where we proved the VADB convergence implies the volume preserving intrinsic flat convergence. And after that, then I'll return to the more complicated notion of integral current spaces and discuss some more of the properties of intrinsic flat convergence and volume preserving intrinsic flat convergence. So let me just remind you that volume preserving intrinsic flat convergence means that you have flat convergence or swift convergence of the MJs to M infinity, and the volumes are also converging. And remember that the intrinsic flat distance or swift distance between two Riemannian manifolds is found by finding distance preserving maps phi I from Mi to Z. Z is any complete metric space. And then we measure these volumes of A and B, which fill it in. So B will be one dimension higher, and the boundary of B should sum up to M1 minus M2 minus this extra part A. And we'll make precise estimates of this form today in order to estimate the intrinsic flat distance between two Riemannian manifolds. Perhaps the hardest part of finding these metric spaces Z is not so much the construction of the higher dimensional part as it is trying to ensure that these are distance preserving maps. So that's perhaps the hardest part. We have to make sure that the distances between points in Z exactly match the distances between points before. So we can't have any shortcuts inside Z that are shorter paths than going straight from here to here. So to estimate the swift distance between two manifolds in joint work with Sajjad Lakhsian, We assume M1 and M2 are oriented pre-compact Riemannian manifolds. That means their metric completions are compact with diffeomorphic subregions Wi contained in Mi. So the reason we say pre-compact here is we're allowing the removal of singular points so that we have nice smooth Riemannian manifolds. So just cut out any cusp or cone tips or even any edges if you have to, okay? And then you have your pre-compact Riemannian manifolds. Then you measure the distance between them, and then you worry about whether those points should have been added back in or edges after doing this estimate. So this particular case, we're going to assume that there are subregions Wi sitting in the MIs, which are diffeomorphic to each other, but the rest of the manifolds don't have to match in topology at all. You may also have loops or wells or things in the MI that are not included in this nice regions Wi. The Wi's are not only going to be diffeomorphic, but they're going to be diffeomorphic to a common region W, but the relationship between the two metric tensors is going to be off by only a very small factor of 1 plus epsilon. So what we think of here is you imagine that W1 and W2 are actually equal to W and that they just have two different metric tensors on them. This way I've already incorporated the diffeomorphism. I pulled back the metric tensors to both sit on the same W. I don't know French that well. There's a question in the chat.
I think it's a mistake from the.
Oh, it's a mistake. Okay.
It's not important.
It's not important. All right. I'm sorry. My French is not so great unless it's very mathematical. All right. So we assume G1 and G2 are different metric tensors on the W. That's how we're drawing this, so I don't have to pull back and write pullback symbols. And so the G1 and the G2 are closely related scale-wise and off by 1 plus epsilon in both sides, and taking the intrinsic diameters to be less than or equal to D. So we're going to assume that the diameters are uniformly bounded. Even if, let's say, one manifold has deep well, the wells will be controlled by this D. And then we define what we call the hemispherical width. Now the hemispherical width is being set up here so that our plan is we want to transition from W1 to W2 with some sort of region that will be part of our Z, okay? And what we want to do is we're going to take A large enough, and this A has been designed to be large enough so that if we were to curve in the metric tensor on W1 in a way such that it doesn't curve faster than a hemisphere. So we're keeping G on this warped region. So this is a W cross 0 to A for this A. And we're requiring that G is bigger and equal to dr squared plus f squared of r GI, where GI is the metric here and the metric here. It has to be bigger than both. And the f of r has to be bigger than the maximum of cosine r and cosine a minus r. So that's why, so that we have this feeling of it's being kind of like a hemisphere. So the W1 looks like an equator for a hemisphere. And W2 looks like equator for a hemisphere. And then, of course, we want to create a G that's nice and at least C0 that stays outside of this hemisphere and outside of this hemisphere. And in this way, we're ensuring that points in W1, distance between points in this one connected component of W1, will not be connected faster than if you just stayed in W1. So just like in a hemisphere, the equator will achieve the distance between them in the larger space. And then we're also guaranteeing the same for W2. And the idea is that we want to take a G that's just large enough to manage this and then actually be continuous and meet up over here. All right, so we prove that we can construct such a G as long as we make the A this large. But this is only going to handle connected components of the W1 and W2. And if there's more than one component, we may have more difficulties. So we're going to have to make some more estimates. So now picture we have, this is my picture from before, and this is our A, and this whole top is the same as before. But now let me draw a picture over here where you can see that W1 might have two components and W2 might have two components. And now our concern is if we have 2 points in one of the components, we know that the way we chose this A guarantees that we're not going to get shorter staying from here to here. However, now we have to worry if we have two different components of W1, that maybe if we went down here, we could cross over in M2 and come back up and have a shorter path than if we just stayed on top. This could happen if the different components of W1 have a very long tunnel between them, and the different components of W2 have a short tunnel between them. So we're concerned about the fact that there might be a long tunnel up here and a short one down here. To handle this problem, we decide that we will define a function lambda, which is the sup of over x's and y's and w of the difference in the two distances. So the difference in the distance here in M1 between points in W and the distance measured in M2 between points in W. We're only checking the x and y's in W. We don't care about any other x, y's that are on the tunnels or on extra wells. We only care about x's and y's that are lying inside the W, and this was really a concern, not about an x and y that are in the same component, but about x's and y's that are in different components. So we just want to make sure there's no, this tunnel is not much shorter than this path, and that this path is not much shorter than that one. And we insist that this lambda should be, we know that this lambda should be less than or equal to 2d, because at worst it would be the diameter plus the diameter. Then we're going to define the height to build up our metric space C. So our original plan was to just make the height A, and that was good enough for each component. But now we're going to add some more height over here. So this is like that piece, W cross A, and another connected component, W cross A. And now we're going to add some additional height here and here. That will make us high enough so that it will never be faster to go down here and up. It will always be faster to go across the top. This height will then depend on lambda so that we can guarantee that. So we computed this, and we found that if we choose our H bar to be this maximum, which depends on diameter, it depends on the lambda we just chose, and it also depends on these epsilons that were our distortions up here. If we choose H bar to be this max, and then we construct a Z that has a height H bar, then this height A, and then an H bar again, H bar, A, H bar, high. So we construct C to be M1 at the top, that's here. Connect to W1 cross the H bar, that's this little region here and this little region here. Connected to W cross 0A, that's warped so that it has this pattern that we already discussed with the hemispherical patterns. We put that here to glue from W1 to W2. And for each connected component, we glue separate gluings. And then we attach to W2 cross 0H, so we make the W2 high enough away from there. That's also to deal with not having shortcuts running down from the top to over. And then finally, connected to M2 itself at the bottom. And if we take Z to be this, where this light blue part is a isometric product, it's a rigid product with no warping happening. And this W2 part is a rigid product, no warping happening. So it's a straight thing. And the only warped region is this part in gray in the middle, so to adjust from the two metrics between W1 and W2 in each component. If you can take Z to be this space here, then you can estimate the flat distance from M1 to M2 by drawing in the same idea we had before, where we fill this area in with B and we fill this area in with B. And then we have the boundary of B will be the M1 minus M2, plus we'll have these little green parts on all the different places. So let's just look at this. I think I have another slide that has things underlined. So let me see if I go to that. Yes. Okay. So remember, we're filling it in with the yellow fat region B. And that region's going to have a volume that's bounded above by the volume of W1 plus the volume of W2. That's an overestimate here, times the heights here. That's an overestimate on the volume of B. And then we have to estimate this part of the volume of A, which is the part that is from the boundary where we cut W1 off from M1 and we cut W2 off from M2. And we have to cross that for the full height. And so that's the boundary of W1 and the boundary of W2 added up times the heights. That's the volume of this light green area. And then for the rest of A, we have this dark green part, which is these extra parts that are the the paths or tunnels in M1, the tunnels in M2, and these extra wells that might happen in M1, all of those parts, which are the M1 takeaway W1 parts and M2 takeaway W2 parts, these two volumes get added. They are not multiplied by the height because they don't get, they're just on this level, right? So then we have the intrinsic flat distance is equal to this. This is the estimate that Lexian and I came up with, and this estimate is used to prove many of the samples I gave in lecture 2 of sequences of manifolds with scalar curvature that I told you in converge in the intrinsic flat sense. This was the actual estimate we used in order to prove that. Are there any questions? Okay. In order to actually apply this estimate, what you basically have to do is you have a sequence of MJs converting to an M infinity, and you have to sort of decompose it into sort of thick and thin regions. And the thick parts will be parts of your W's. Now, that can be very difficult to do explicitly unless you know more about the manifold. And that's why many of the cases have only been done in special cases where we assumed more facts about our M1. Generally, what we do is we estimate explicitly MJ to an M infinity that we've already guessed. So you take a sequence, you draw the pictures, you guess what the limit should be, and then you take a sample MJ, arbitrary J, and the limit space, and you start dividing it up to make the proof. You start cutting out the W's, estimating the areas, the boundaries of W's. Sometimes you need a sort of choose better W's just to get the boundaries more under control. So sometimes you will leave some of the thick region off just to make this boundary better, but then you have to compensate because when you put too much outside, you can't have too much volume here. So it's a balancing act, but you can do this explicitly from many examples. All right. However, it is very difficult to use this when you don't have much information about MI and you cannot picture the MI. So that's why we actually proved this theorem with Allen and Perales. So that's Brian Allen and Raquel Perales. I think Raquel is here. I didn't see if Brian is here. He might be teaching at this time. I don't see Brian here. This is Raquel. She's here and she'll be speaking next week. Yeah, Brian must be teaching right now. So anyway, the idea of this was to come up with an easier way to prove intrinsic flat convergence or volume preserving intrinsic flat convergence, where you wouldn't have to know which regions were good and which regions were thin. You could just have overarching facts about them. And we came up with the idea that if you have volumes converging to the limit volume, and these are Riemannian manifolds in this picture, and that there is a D that's uniform where the diameter is less than or equal to this D, and there's a C1 diffeomorphism psi j from M infinity to Mj, such that the distances in the sequence are bigger than or equal to the distance in the limit. So we have volume above, the volumes are converging, and distance below. So the distance are estimated from below. We don't have to know which regions are fat and which regions are thin. We don't have to know how to divide our manifolds up. We will get the theorem, we'll get the theorem that will have the volume preserving intrinsic flat convergence from this. And this is very useful and has been applied by Cabrera-Pacheco, Perales, and Ketterer to prove the torus geometric stability of the scalar torus conjecture in the setting where the manifolds are assumed to be graphs. So how are we going to prove this? Is there a question in the chat? No. Okay, I don't know why that came down. So an earlier theorem that inspired us was this theorem by in a paper by Huang Li and I, which was studying the positive mass theorem when the mass is very small in the graph setting. And as a step of our proof, we came up with this method for estimating the intrinsic flat and Gromov-Hausdorff distance between things. On some level, the Gromov-Hausdorff result was already known. The intrinsic flat was not. I'm just going to mention this theorem because it was inspiring to us. In this theorem, we actually have dj over d0 bounded above and below. So this is not volume above distance below. This is distance above distance below. Okay, so this is saying that we have these DJs are not controlled this much. And then we said the DJs minus the D infinity had to be within epsilon J. So notice what's interesting is there's a D infinity here and there's a D0 here. This D0 is used to estimate the distances, the ratio of distances, but the closeness of DJ to D infinity is only a difference, which is similar to this. It's only a difference in the distances. And we're able to prove that we get intrinsic flat and Gromov-Hausdorff. For Gromov-Hausdorff, you don't need this extra part, but for intrinsic flat convergence, we did need this ratios in this original proof by Huang and Lee. This is in the appendix of our paper. So this is a theorem that inspired us, but we wanted to remove the fact that we had so much control on the distances because this was so strong that we got Gromov-Hausdorff convergence as well and didn't allow for wells. So what we would like to do is loosen this up and only have the volume from above and the distance below. We do require the C1 diffeomorphism exists. That's sort of replacing this part. This is like saying, oh, we have at least a C1 diffeomorphism. But our C1 diffeomorphism here is not required to have any uniform control on a lambda. We're just saying it exists. And the fact that it exists is enough for us to start talking about the chart structures going back and forth between the two spaces. All right.
Cristina,
Yeah.
it's Andrea, just one question. Would it change very much if instead of asking C1, you ask for B Lipschitz, the psi?
You'll see where we use C1 because I'll go over the proof.
Okay.
We have in fact used C1 in a way where I think it's mostly important to get the infinitesimal Euclidean structure matched up, but we're actually kind of using it for Jacobi fields.
Ah, okay.
Yeah.
Thanks.
So I imagine that we could loosen with significant extra work, could change C1 to by Lipschitz. But that would take significant extra work. And I'll point out the step in the proof where we did that.
Okay, thanks.
All right. Anyone else? Okay. It also is interesting if you're inclined to like be skeptical when reading a proof, that you can watch this and see if maybe you can show, you can think of an example that's a by Lipschitz that's going to fail. We use it, these are both Riemannian, and it's a C1 diffeo. If you like Finsler's, I bet you could find a counterexample if you assume it's Finsler. All right, that would be a nice publication for somebody to show that this really needs Riemannian. Okay, so here's the statement of our theorem. I just wrote it again, so we have it handy. It's exactly what I just wrote, but I added a precise estimate on what the intrinsic flat distance is going to be here. So, sorry, this is not exactly what we just wrote. Let me go back here. What we wrote here was volumes above and distances below. This new part is, we're going to assume that we have the C1 diffeomorphism, we have the volumes and the diameter is controlled like this, and we have the distances bounded below. But now we're going to say, suppose there's a WJ that's a measurable set, and assume that there's a delta J greater than 0, such that we have DJ greater than equal to D naught plus 2 delta J. So we're having a distance above on a WJ. So this is a little bit similar to the estimate Laxian, and a little bit similar to the estimate with Huang and Lee. We do have distances on both sides. We have the volumes less than or equal to Vj also, and we get the heights because we're going to actually literally construct a Z and we're going to use this heights. This height is very similar to the one used with Sajjad Laxian. And then we get the intrinsic flat distance will be less than or equal to twice this Vj. This is the extra pieces plus the HJV, which is like the volume of the V part. You'll see, I'm going to draw the pictures. So here's our MJ. Let's pretend it has some wells that I've drawn in yellow. And here's the M0, who's nice and well-behaved limit space we're going for. We're going to define our Z to be a copy of MJ cross 0H for this H, HJ. So this is the Z, and you see that he has these bumps out for the wells of MJ. So Z actually looks a lot like MJ with all these wells sticking out. And then this is the middle of Z. The top of Z, we're going to glue MJ cross 0H to MJ, but we're not going to glue the wells. They're left loose and open. So we're only gluing it along the nice set WJ. And M0, we glue this to M0 everywhere. So that pulls this tight. So if you think of this as a sheet of paper with some wrinkles, we don't glue the yellow wells in, and we do glue everything tight to M0. So there, Z is MJ glued along WJ to MJ cross 0H and glued along the image of FJ WJ to M0. Okay, so let me just, this is the justification for this statement we have here, okay? Once we can manage this, we prove that this is distance preserving, then our flat distance from M0 to MJ is going to be our B that we're going to fill it in will be this vertical part. So that will be our MJ cross 0H, which gives us HJV as our upper bound on the mass of B. And then we're going to have boundary parts, and we estimate that the boundary parts, well, we're going to have a boundary part down here and a boundary part going up here, and we'll have boundary parts going down here and boundary parts going up here, and those will cause a 2VJ, where VJ was basically the volumes of the wells that are yellow. It's double them because we didn't attach them. All right. So now we would like to use this, we would like to set things up. So if we have volume above, distance below, we can apply this estimate on ZJ. So to get this, we need to control, we have this already in our theorem, distance is below, but we need to get this distance above estimate on some set WJ in order to complete the theorem of VADB implying VF convergence. So the first step was an older theorem I proved with Alan in a different paper, where we said that if we have metric tensors GJ greater than G naught and the volumes are converging, then we get the limit as J goes to infinity of the distance from P to Q is equal to distance in the limit PQ pointwise almost everywhere for P's and Q's in M cross M. Okay, so this is actually kind of straightforward, integrating volume forms, integrating out. And the problem is that we're getting pointwise almost everywhere for pairs in M cross M. But what we need is a large enough set where this will be uniform convergence on a large set, not in M cross M, but a large set in M for all the PQs, P's and Q's in M, not pairs PQ in some subset of M cross M. Here's a picture of what we have to do the proof here. And this is the very Riemannian part. So this is the proof for this theorem, why this is enough to get this DJ. Suppose we have a collection of points here, a union of points here and points over here, a tube tau foliated by G0 geodesics. So we're using that the limit space has geodesics with length J gamma greater than or equal to length 0 gamma. That's going to come from 85 here. And volume J tau going to volume 0 tau of this tube. The volume of the tube is converging to the volume of the tube. If the volumes are converging, you can show that the volumes of the tubes also converge. Okay. So we have this tube here of geodesics. And the lengths of all of them are longer than the lengths of limit space. The limit space is the red ball. So we're picturing sequences with increasingly many wells, and they're converging to the red ball. And we're looking at tubes in the sequence. And we're asking, okay, the volume of these tubes is getting closer and closer to the volume of corresponding region in the red ball. And the lengths of all these geodesics is bigger or equal to the lengths of their images in the red ball. And what does that tell us? That tells us that the length of each of the geodesics converges to L0 for almost every gamma, but not for a gamma ending in a tip. So you see there can still be some long ones. So we can use this given here to force that most of the gammas will converge to a limit gamma. And then we do this for every tubes, and we keep working and keep working. That's where the pointwise almost everywhere is coming in. It's really like pointwise almost every gamma, every geodesic gamma between points in M cross M. And because of that, it's P comma Q in M cross M. Any questions? Okay, but now we want to find the W and M so we can construct our space Z. And we need to control DPQ for all P's and Q's in W. And so far we have almost every pair PQ in M cross M. That is not close to having a W where all the PQs in W have distance controlled. We would like to use Egoroff's theorem, but Egoroff's theorem only tells us that we have a set S in M cross M where DPQ is uniformly controlled for all PQs in S. So Egoroff's theorem is the standard theorem that says that if you have something almost everywhere, you can get a large set where in the region that we're talking about, where we can control the distance uniformly on that set, but it's a set sitting in M cross M, not a set sitting in M. So here's what we get from Egoroff's theorem. We now have that under the hypothesis of our theorem, for every epsilon, there is some volume G naught measurable set S epsilon, considering an M cross M, such that the sup of the distances with PQ and S epsilon equals some delta epsilon J goes to 0, and the volume of S epsilon is bigger than 1 minus epsilon, the volume of the M cross M, so it's almost the whole volume, and PQs and S epsilon if and only if Q and P are in S epsilon. So we have the symmetry. This extra symmetry comes from the fact that it's really about gammas. It doesn't matter which way the G at S of gamma goes. All right. Now let's define another set, SP epsilon, which are Q's and M's such a PQ is an S epsilon. So for each point P, here's my point P, for example, in this. So I'm taking, I'm just fixing this well, the one with the many wells is our MJ that's pretty large, and our M infinity is again a sphere. And SP epsilon is, here's our, if this is my point P, this is all the Q's such that P comma Q is in this S epsilon set. All the Q's where you have distance control for that P. Then over here, if I choose this P, there's almost no Q's. It's a very small. This is not a good P. This is a bad P. It has, when the P's lie in wells, you have very tiny collections of Q's that behave well. Tiny little regions around them where the P comma Q is in S epsilon. And if P is over here, then there's a nice huge region, again, where PQ is in S epsilon. So we're seeing that for many P's, we have a very large SP epsilon. 1 minus epsilon of the volume 0 of M is less than this integral of the volumes of the SP epsilons over the volume M. So integrating over all P's, we have a large volume for these SP epsilons. So if you're on SP epsilon, your distance PQ is controlled for P. We now need to find a W where distance PQ is controlled for all P's and Q's in W. So to do that, we take our W to be the collection of all P's where the volume 0 SP epsilon is big. So this won't include any of the P's that are inside the wells, but it will include P's that have a nice huge volume for their SP epsilons. Okay, the epsilon is about how close we are and how well behaved things are. So now I'm only going to choose the P's that have big SP epsilons. And we show that the volume 0 WK epsilon is bigger than this. So this is all in the work with Allen and Perales. And we have the distances are controlled on this WK epsilon. The K here is how good the estimate is. Well, that's exactly what we needed. We needed a set W that was nicely behaved for all P's and Q's in W. So by only choosing our large volume guys, we're actually able to control all the P's and Q's in that W. This eliminates P's and Q's that are on the wells. This eliminates it in a way where nobody else has to find the wells ever again, right? This is eliminating it in a general way where no one has to identify where the wells are. We now know that there is this volume, this set who has a large enough volume and the distances are well controlled. It exists. Well, once we have this set, this guy here, I just split it up. We combine this with the estimate where we constructed Z before. This is the one I said where we constructed Z and we're able to compute the intrinsic flat distance. So we combine this lemma with this theorem earlier. And that completes the proof that MJ VADB converges to M infinity implies that MJ VF converges to M infinity. We have the intrinsic flat from here. Our VJs have to do with how close the volumes of W's are close to volume 0. All of the estimates have to be done carefully, keeping track of the K's and the epsilons and the J's carefully. We're able to get the C and we get intrinsic flat convergence. And then to see that the volumes converge is not so hard because we can just estimate the volumes converge from the given information of our whole problem. Remember, we assume the volumes converge. So that gives us the volume preserving intrinsic flat convergence. Any questions? All right, so this is now a very useful theorem that should apply in many of the cases. It's only been applied to prove the VADB convergence and thus volume preserving intrinsic flat convergence for torus almost rigidity, torus geometric stability of the torus rigidity theorem by Cabrera, Pacheco, Perales, and Ketterer for the tori that are graphs. Other cases have not yet been used. This has not been applied to any of the other geometric stability theorems. It should be applicable to anyone. If you wanted to try the geometric stability theorems in the graph setting, you could imitate what they've done, and you could look at one of the other geometric stability theorems and write out how that theorem can be rewritten using a graph setting, a graph where the manifold MJ sits as a graph over M infinity, and work it out. So I do believe this should be useful in many of the other cases, and it would be a very nice project. And it would be a full paper to do it. All right, so now we're going to switch back to integral current spaces and continue where we left off in the fourth lecture. I will review what we discussed in the fourth lecture, and then we will continue forward. All right, so to do most of the projects, you only need the previous theorems. And then this collection is to fill you in on really what properties you're going to get once you do have swift convergence or volume preserving swift convergence. So recall you have flat limits of oriented cell manifolds are called integral currents, and then Ambrosio-Kirchheim defined an integral current in this way. An integral current is an integer rectifiable current T, whose boundary is also integer rectifiable. And integer rectifiable means you can find countably many pairwise disjoint by Lipschitz charts, just that they exist, not that we actually know what they are, and weights AI in the integers, and that we can write T acting on a tuple of Lipschitz functions here, T of F pi 1 to pi m. So F is a bounded Lipschitz function, and these guys are Lipschitz functions. They are functions that are defined on Z and have real values. And T acting on them is defined to be the sum of AI, that's AIs are the weights in integers, integral over these capital AIs, which are Borel sets in Rm, the M that matches this M, of F pull back the phi, d pi 1 pull back phi, d pi m pull back phi. All of these guys are Lipschitz, therefore they're differentiable almost everywhere on the AI, and we can do this integration. This integration is done on a Borel set in Rm, so it's well defined. The mass of these sets is the mass measure T of Z, where the mass measure equals some lambda, which is called an area factor, that was bounded above and below by constants depending on dimension, theta, which was a weighted function, which depended on the AIs, and the Hausdorff measure of M restricted to the set of T. The M again here is matching the dimension of the integral current, is matching the dimension of the tuple. And the set of T is the set of positive density. It's the points where the measures of balls divided by Rm comes out to be greater than 0 as you take R to 0. This is just ensuring that it's not a cusp tip. It's a cone tips are included in the set. Cusp tips are not included in the set. The reason we use the set is because the Ambrosio-Kirchheim proved that the set is integer rectifiable as a set, which means it's actually covered by these disjoint charts, disjoint by Lipschitz charts almost everywhere. Okay. The closure of the set, which is called the support, is not necessarily covered almost everywhere by Lipschitz charts. The closure of the set could be even have higher Hausdorff dimension. The set is the one that's covered almost everywhere, and that's why we use the set of positive density. The key idea is that integral currents generalize oriented submanifolds in Z, and the new idea was generalizing oriented Riemannian manifolds, so we needed to have separate spaces. And so Wenger and I defined an integral current space to be a metric space XT with this integral current T, and we require the integral current T to have its set equal the entire X. So X becomes a rectifiable metric space, and it is covered by the charts almost everywhere. Furthermore, we define the mass of T of the integral current space just to be the mass of the T, and that the boundary of the integral current space is the set of the boundary T with the D restricted from M and the boundary T here. So the D is always restricted from the larger space. This boundary of M might not be connected. Neither does an original space have to be connected. But even if the original space is a Riemannian manifold, if it has two connected components for its boundary, the boundary is a single metric space, and each connected component still has distances between them where the distance travels inside M, not inside boundary M. And so this may not even have any geodesics if all paths between points in the boundary are connected by minimal geodesics in M. This distance will actually be smaller than a geodesic distance here. All right. So X is countably HM rectifiable, it has all these disjoint charts, and they cover almost everything. Okay, we had the same slide before. An oriented Riemannian manifold is a metric space with smooth collections of charts. Distances are defined as infimums of lengths, and the volumes are Hausdorff measures. Integral current space is a metric space. It has an integral current, which means that there exists countable collections of charts, right? But they're weighted and they have orientations. And the set of T is equal to X. The set is the positive density, so it has countable collection of Lipschitz charts, and they're oriented weighted. The mass is this formula. It might not be connected, and it might not have any geodesics. So this is not the formula for the distance anymore inside an integral current space. Its boundary is defined this way. And a compact oriented manifold gets described as an integral current space MdM. And this integration defined by the charts on M, it has weight theta equal 1 by definition, and that the mass of U comes out. If you then work it out and do this, you'll end up with lambda will be 1, the theta will be 1, and you get M of U equals volume U is Hausdorff measure of U. And the boundary is this, which has a restricted distance dm. It will also turn out to have weight 1 with some extra work, and the mass of the boundary will agree with the volume of the boundary. The Hausdorff measure of the boundary, 1 dimension lower. When I say oriented here, I just want to emphasize again, there's a distinction between the manifold and its opposite orientation. They are two different integral current spaces. All right, now the intrinsic flat distance between two of these spaces is defined this way. We talked about last time, where you look at these guys as weighted integral current spaces, you map them with distance preserving maps. The distance preserving maps is the only part where we use the D1 and the D2 to define distance preserving. After that, we look at the push forward of the charts and the push forward of the charts, and we just estimate the infimum of the mass of A plus mass of B such that we have the subtraction. If you change the distance, the only thing that changes is the distance preserving maps. If you keep the distance the same and you change the integral current structures, then you'll have the same distance preserving maps, but the integral current structures might have completely different A's and B's that fill them in. All right. Inside the original paper with Stefan Wenger, we showed that the infimum is actually achieved for this definition. So there's actually a Z and there's actually an A and a B sitting in Z that achieved to be exactly equal. The mass of A plus mass of B is equal to this infimum. And because we're able to show this, we can take a new set Z prime sitting inside Z that's equal to the set of A union the set of B. The sets of positive density for those two guys. This Z prime is separable and rectifiable. The original Z was just complete. So this Z prime is somehow more useful. And this means that the infimum could have been taken over such Z primes that are separable and rectifiable. Okay, so that's a nice fact that this definition could have been made with separable and rectifiable Z's. And we're going to use that to glue together a limit. So if we have MJ swift converting to M0, there's a complete separable Z and distance preserving phi J's such that they converge inside the Z. So we're going to create a single Z for the entire sequence. So that was found. We talked about that. What we did was we glued together all these Z primes for each J, and we were able to glue them all together to get a new separable Z with distance preserving phi J's into Z. So we have a common space Z, and inside Z, the flat distance is going to 0 for the images. And when you test them against tuples, they converge as well. This is called weak convergence occurrence. Now, Ambrosio-Kuerheim theory has a lot to say about sequences of currents that converge inside a complete metric space Z. We can easily take the metric completion. So we have complete separable Z here. And so we can apply Ambrosio-Kuerheim theory to these push forwards sitting inside Z. So that means that we get boundaries converging to boundaries. And we have limits of the masses is bigger than the mass of the limit. So this is using Ambrosio-Kuerheim theory and the fact that we have the single metric space Z that everything fits inside. Then there's a theorem that's in my paper with Arzello-Ascoli in the title that says for any P and M infinity, there are PJs and MJs such that the distance in Z between phi J PJ and phi infinity P is going to 0. So that's sort of saying that we have points in the MJs that converge to the limit point. How do they converge? They converge in the sense that if you choose this guaranteed existing distance preserving maps, their images under those, the maps here, are going to 0. This notion of PJs converging to P is going to depend on your choice of phi J's. It depends on the choice made in this theorem. Then there's an Arzello-Ascoli theorem, which is perhaps the main theorem from that paper, and I didn't tell you this one before. So suppose the MIs are integral current spaces, and MI is flat converged to M infinity, and FI from XI to W, from these to W, are Lipschitz maps into a compact metric space W, where they have a uniform bound on their Lipschitz constant. So these are the functions we're going to use. We're going to do on Arzello-Ascoli too. So this is an Arzello-Ascoli theorem. We have uniform bound on their Lipschitz constants. A subsequence converges to a Lipschitz map F infinity who has the same bound, and he goes from X infinity to W. So it's an Arzello-Ascoli theorem. When do we have sequence of functions? Have a subsequence that converges. Now, what does it mean to say it converges? It means that if I take points in a point in M infinity, there are PIs going to that point. Fi of PI is going to converge to F infinity of P. That's what we mean by converges. That choice of how the PIs go to P infinity depends on the embeddings from the previous page, but the existence of F infinity is then established and we can use it without discussing the points converging. The main application of this is to say, now I have by Lipschitz, a Lipschitz map that goes to an image. This is the explanation of what we mean by the converging with a sequence of points here, converging to their images, but the main point is you now have this Lipschitz map at the end. There is an Arzello-Ascoli theorem for Gromov-Hausdorff convergence. I actually included in the same paper. I review it. It's a commonly used theorem. I just wrote out the proof of it there because I couldn't find the proof of it in the literature. For the Gromov-Hausdorff version, the xi's converge to X infinity in the Gromov-Hausdorff sense, and you can even change the wi's, and they can Gromov-Hausdorff converge to W infinity. For the Gromov-Hausdorff one, you can have both the domains and the ranges converging. But for intrinsic flat convergence, you can only have the domains changing. There are counterexamples if the ranges change or codomains change. The counterexample that's obvious is assume xi's are all the interval 0, 1, and that the fi's are geodesics running between 2 points. in the WIs. The WIs could converge to a space that has become disconnected, and then there will be no limit f infinity that runs from an interval to the disconnected space. So this is the strongest possible. We can only change the domains, and we cannot change the ranges. The range has to be a fixed, constant, compact metric space for this theorem. All right, there is actually another theorem in the paper where both the domains and the ranges change, but it has extra conditions on the range. So you can look at the paper, it gets rather technical, what we need to do to prevent that breaking of the range. In particular, we study the case where FIs are local isometries. All right, so enough about that. We also, in the Arzelà-Ascoli theorem, talk about balls and Swift limits. So if BPR is a ball in integral current space, then this we can create an integral current space out of a ball, which is the ball itself, distance on M, and this integration over the ball is an integral current space for almost every R greater than 0. In the paper with Wenger, we have that if MJ Swift converge to M0, there's this complete separable space, right? And all of them converge inside that space. So I'm going to use that one again. If P0 is an M0 and MJ Swift to M0, we have the points converging inside this, using this collection of phi j's. So these are all three theorems you already know. And I want to put them together. So for almost every R, there's a subsequence JK such that the subsequence of the balls Swift converge to the limit ball. Now, there's almost every here because there's an almost every over here that the balls even exist. And there's a counterexample in the paper to demonstrate why you need almost every. As a corollary, we know the limits of the mass of the balls is bigger than the mass of the limit. We know that the boundaries of balls converge to boundaries of balls, assuming we're already in the subsequence. And that the filling volumes converge to the filling volume. We defined filling volume in lecture 4. The diameter of M0 is also less than or equal to the limit for the diameter of the MJs, which is also true for the balls, because we have these distances. It's possible there are points in the MJs that disappeared at the tips of wells. So these diameters could be significantly larger than this final diameter. There's only a limit. And then we have a theorem that says if M swifts to M infinity, you can actually find domains NJ and MJ such that NJ's Gromov-Hausdorff converge. So think of this as we know that there exists a region where we've cut off the wells and that this region actually converges in the Swift sense to the limit guy. And in addition, the limit as J goes to infinity of the mass of the NJs is bigger than the mass of the Swift limit. So it's actually quite large. These are large NJs. They have large mass or large volume, including the weight. And the Gromov-Hausdorff converge. So this is sort of like a theorem that says you can actually cut off the wells and find a Gromov-Hausdorff converging region inside. All right, I think I told you most of this already. I need to review it now because we're going to use this. Are there any questions? The main takeaway is we have a way of saying points converge to limit points. That depends on how we choose our phi j's and how we choose our z, but that the ultimate answers that come out of it are useful to us, even if we don't know what the pj's are or what the p infinities are. We can draw the pictures and ultimately we can say which points are going to disappear or not, depending on the filling volumes of the boundaries of the balls. Certainly, if the sequence pj disappeared in the tips of wells, the filling volumes will end up going to 0. But if they don't disappear, the filling volumes converge to something positive, which is the filling volume of the limit. For R small, this filling volume will definitely be positive. The proofs of all of these theorems use Ambrosio-Kirchheim slicing theorem, which I told you about last time, and now we didn't continue beyond that. We stopped at the slicing theorem. So let's recall the slicing theorem. The slicing theorem says that if you have an integral current T inside a complete metric space, and you have a function here that goes to the reals, that there's a way to define a slice, TFS, which is essentially sort of like the intersection, roughly. Intuitively, it's the intersection of this submanifold with F inverse of S. It's going to be this line. All this extra work is to give it appropriate structure as an integral current, okay? So that it has a notion of direction and how should it act on a tuple. If T was a submanifold, the slice TFS is simply the submanifold intersected with F inverse of S. And for almost every S, that will be a one dimension lower, and that will be well defined as an integral current. The fact that we have to do this T intersected with F inverse S infinity is just sort of to narrow it down to this part. And then boundary T intersected to that is to say, oh, the boundary T is just this part. And we subtract it just right so that we get this direction on our slice. And to prove it's an integral current, they prove its mass and the mass of this boundary, which they work out. Boundary of TFS is equal to negative boundary TFS. That's finite for almost every S, and they prove this integral. Now, I'm not going to prove the Ambrosio-Kirchheim slicing theorem. You can find it in their original paper in 2000 in ACTA. What we're going to do is use this theorem. So we're going to apply this theorem to get results. Any questions? All right. Let me just say, remember I said we were going to apply this in order to understand balls. So if you have a point in the limit in the space C, F, for example, has to be a Lipschitz function, right? If F is the distance inside Z from a point in Z, its Lipschitz constant is 1. So we could apply this to distance functions about points in Z, which would tell us about the intersections of the images of the manifolds with balls in Z. But our theorems are about sequences of balls in the original manifold. So it gets a little more tricky than just applying this. We have to get theorems about the balls in the original sequence of manifolds where the P's, the points, are changing. And this is about a fixed function. So when we do the slices with a fixed function, we get these nice estimates. But if we have changing functions, things will become more difficult. So suppose we have given integral currents Ti and Z. Now we have T1 minus T2 is A plus boundary B, right? If we've estimated, and the distance between T1 and T2 is mass of A plus mass of B. These are nice facts we have. What do we know about the slices? Well, let's take T1 minus T2, this line here, and let's slice that line. So we slice the first minus the second plus the slice of A plus the slice of boundary B. So this is true about the slices. Now let's write what that means. So the first guy still has his own slice, the second one is his own slice, and A is his own slice. But remember, we figured out the boundary B sliced is negative the boundary of the slice of B. Okay, so we have to switch the sign here to match the rule for taking a boundary of a slice. All right, so then the flat distance from T1, this slice to this slice, is less than or equal to the mass of this slice plus the mass of this thing here, BFS. Okay, so now we have an estimate on the flat distance between these two slices. Remember, this formula is only for almost every S. All of these are for almost every S, and so is this, almost every S. All right, I maybe did too much at once. Let's say what we know about masses of slices. We can use Ambrosio-Kirchheim's integral and say the mass of the slices of A integrated is less than or equal to the Lipschitz constant for F and the mass of the whole A. And the mass of all the slices of B integrated is less than or equal to the Lipschitz constant of F times the mass of B. So we end up that the integration of the flat distances, if we integrate the flat distances, is less than or equal to lip of F plus this sum of the masses. So that means the integral of the flat distances is less than or equal to Lipschitz function times the flat distance from T1 to T2. Okay, because remember, mass A plus mass B was achieving this flat distance from T1 to T2. So now we have this estimate on controlling the flat distances between slices. So we have that if DFC, the flat distance between TJs to T infinity is going to 0, and F has Lipschitz F less than or equal to 1, then we get this integral converges to 0. So for almost every S, there's a subsequence such that each one of these guys converges to 0. That's how we can remove the integration. But what about slices converging that are in integral current spaces, where the slices, okay, so we want to, now that was all sitting inside Z. This is all sitting inside a metric space Z, but now we want to talk about sequences of integral current spaces. So I'm going to define the slice of an integral current space is equal to the set of the slice of the T for the integral current space, D, and the sliced integral current structure. It's a typo here. This is slice. Okay, no, it's not a typo. This is a definition. Slice of integral current space x dt with function f with s is equal to the set of the slice, the distance from x, and the slice is defining the current structure. This is defined for f being a function that's Lipschitz on x itself. So if these guys Swift converge, then there's a Z, and we can put them all into the same space, and we can talk about these push forwards. And then we can apply this theorem to these push forwards. This TJ should be big. So if we take Fj equal F following phi j, if all these functions on each one of these guys is actually a function on Z following the embedding map, we would get that slice MJ, Fj, S Swift converges to slice M infinity, F infinity, S infinity, exactly using what we wrote up here. But this only works if I have Fj equal to F following a phi j. So if all the Fj's come from an F on Z, an F here that's on Z, then we can do this, but otherwise we cannot. Is someone chatting or asking a question? All right, so this is already useful if for some reason you already know the embeddings into Z and you put a function on the Z space, you could use this. This could be useful to you. But in general, you don't know the embeddings into Z, so you can't define functions on the manifolds that depend on the Z embedding. You need to tell me, we want to know things about balls inside MJ. We want to slice about using Fj to be distances from points inside MJ, and for everything to switch, not a sequence built that just applies this theorem. So with Portuguese, after significant work, we're able to prove that if PJs or MJ converge to P infinity and M infinity, then for almost every S and R, a subsequence of the slices where this is the distance function from PJ converges to the slices where this is the distance function from P infinity. We use this as a step in the proof, but then we also have to estimate what happens when your function is changing. Our functions are changing because distance from PJ and distance from P infinity are two different functions. So in order to complete this proof, we actually have to also integrate over changes in which function is doing the slicing. This is the key step in the proof that balls converge. So balls Swift converge and boundaries of balls Swift converge. Again, almost every S. All right, so now I've finally proven why, or roughly proven why, we have balls converting to balls and boundaries converting to boundaries of balls. Any questions? Also in our same paper with Portuguese, we defined sliced filling volume and we estimate it. Now, slice filling volume is talking about the filling volumes of the slices and how the filling volumes of the slices converge to filling volumes of the slices. And we do this where the functions are defined using distance functions from points. But what we do is we slice again and again. So once you have the slice with distance function converging to slices, okay, so once you have, sorry, let me put it here. The slice with one distance function converting to, this is now a sequence of integral current spaces that converge to this one. And now I can choose another set of points, qj's in here and q infinity, and I can slice the slice. And then we can take another sequence of points, xj's going to x infinities, and I can slice the slice of the slice. And you can take more and more slices and get swift convergence of slices and go down all the way down until the slice is zero dimensional. And then it's a collection of points. And so we use that to get some very interesting results related to the filling volumes of collections of points that are slices of slices of slices. So if I have time at the end, I can tell you more about that. I just want you to understand that once you have a method of slicing, you can do it again and again. Another thing to really keep in mind is the slice is one dimension lower. So if we start, this is a completely m-dimensional paper, and we consider all dimensions m. But for the applications that I brought up in the second lecture, our dimensions are always 3. We slice it once, we get slices that are surfaces that are 2-dimensional. And remember, we had said we wanted to keep track of surfaces because we wanted to understand min A. So you can use slices to help you keep track of surfaces. There's no reason slices have to be defined as distances from points. You can use slices that define other surfaces. And that's why I was emphasizing this point here. You can use any f that's defined in your limit space and get a sequence that converges where your fj's are made from f. Or you can use imitate our proof to try to allow fj's to change even if your fj's are not distances from points. Okay, so you can learn from the proof of these things to try to extend the results to exactly what you feel you need. What do you need? I want to control minimal surfaces. Okay, so what slice should we use to control those minimal surfaces? Are we going to have a sweep out defined like in Marcus Nevis? Maybe your FJs come from the sweep outs that are actually achieving the width. Things like that. Nobody's done this work yet. This is all open for people to do. All of this is explained in the paper with Portuguese and Sormani. Any chat question? All right. So from the last slide, I just copied over this end play about the slices converging and the balls converging. And now I want to talk about volume preserving intrinsic flat limits. This is just intrinsic flat limits without the volume preserving. Volume preserving is going to add more facts and more control. We know without the volume preserving, with just the swift convergence, we'll now have the masses of the balls bigger than the mass of limits and the mass of the boundaries of the balls bigger than the mass of the boundary limit. But if you add in the volume preserving intrinsic flat, we know that the mass of the whole limit is equal to the mass of the whole limit. Sorry, the limit of the whole masses is equal to the mass of the whole limit. So if we combine this with this local information, what do we get? We have the mass of the whole is bigger or equal to the lim of the masses of each term in the sequence. It's actually equal to the lim, but I'm going to use bigger than or equal to lim. And the mass of mj is bigger or equal to the mass of balls in the sequence, bj, and mj taking away bj, the outside of the balls. But the mass of bj's, the bj's converge to b infinity. So the mass of bj is bigger or equal to mass of b infinity. And the mj's taking away bj converge to m infinity, take away b infinity. And those masses will be bigger than the mass of the limit. So we have mass of the whole is bigger or equal to each of these pieces, is bigger or equal to this, but those add up to the mass of the whole. So that means every one of these inequalities was an equality. If we have the VF convergence, everything here is an equality. If we only have swift convergence, we don't have the first line. So now we know that the masses of the balls had to converge to the mass of the balls. Every inequality used here had to be an equality. That includes the inequality from mass Bj to mass B infinity. So now we have masses of balls converge to masses of balls if we have VF convergence. Portuguese uses techniques of Fukaya to apply this to control eigenvalues of the spaces. So if these are Riemannian manifolds, we have the eigenspectrum of Riemannian manifolds, the eigenvalues of the Laplace-Beltrami operator. It's called the spectrum of the Riemannian manifold. And he shows that the lim sup as j goes to infinity of lambda k converges to lambda k of the limit Riemannian manifold. If they're not Riemannian manifolds, he explains what lambda k is. It's a new notion because integral current spaces did not have a Laplace-Beltrami operator, but he describes what these lambda k's are using the Rayleigh quotient. So now we know that if you have VF convergence, the eigenvalues of the spaces converge in the lim sup setting, lim sup convergence, or semi-continuity of eigenvalues, each term by each term. And he imitates work of Fukaya, where he does this in other settings. Juriguet and Lee study this VF convergence, and they're able to prove areas of certain surfaces converge by studying the integrals of the masses of slices. So not just that the volumes of the boundaries of balls converge almost everywhere, which is true, but also areas of other surfaces that were useful for their work. Juriguet and Lee were working on the continuity of the ADM mass, which is a physical notion, and they needed to control surfaces related to that question. They're isoperimetric style surfaces they needed to control. So they were able, it's very nice work. You can see how other surfaces and not just ball shapes can be controlled in this process. Again, using this idea of how all these inequalities become equality due to the absolute mass control of the limit spaces here. Right, any questions? This is perhaps an oversimplification where we do balls. If you want to control areas, you're going to have to use those integrals I showed. The integrals will be bounded, and the integrals will have their integrands bounded below. And then you're forcing the integrals to have all equals. And in this way, you're able to get slices to have the mass convergence of the slices. Okay, so if you can get the slices to converge, you'll get, in general, the limits of the masses of the slices will converge. And now with the volume preserving, you're going to get the masses of the slices themselves to converge to the masses without a limit. All right, so that's an extra strength that is added from the volume preserving intrinsic flat. So what you should think of, volume preserving intrinsic flat convergence makes volumes of balls converge to volumes of balls, volumes of certain kinds of regions defined with Lipschitz functions converge to regions, volumes of regions defined with certain kinds of Lipschitz functions, that you can get slices, which are surfaces inside the manifolds, to converge if they're the right kind of slices and they are under control, which includes boundaries of converging balls. Those areas will converge, and we already have distances converging for points that actually don't disappear. If points disappear, then their distances can be getting large, and that's okay because they're disappearing anyway. All right, so let's go back to this conjecture I mentioned in the very first talk and what we can say now that we know all this information. So in the first talk, we said, suppose we have three-dimensional manifolds and the volumes are bounded above and the diameters are bounded above. And then we said that by Wenger's compactness theorem, subsequence converges in the Swift sense to some integral current space, which might be zero. And we know from my joint work with him that the volume of MJs will be bigger or equal to the mass of the limit. And we know that if M infinity is not zero, it's M rectifiable. This is all known. Now the conjecture is, if in addition we have scalar j greater than equal to 0 and min aj greater than equal to a, and we still have our dimension here, our three dimensions, then the conjecture is that, and let me remind you, the min aj is the minimum area of a closed minimal surface. then M infinity has generalized scalar greater than or equal to 0. But let's talk more about what that means now. We believe that MJ volume preserving intrinsic block converges to M infinity, where M infinity is a connected lane space with Euclidean tangent cones. I haven't really mentioned that before, but actually that is part of this conjecture that we're going to have. I mentioned that we would have volume preserving to M infinity and that we would have generalized scalar greater than or equal to 0. But what I want to emphasize is this conjecture also includes that M infinity should be connected. So we don't have tubes in the middle where things disappear. I mean, obviously you could draw those if you didn't have the min A, okay, that it's connected and that there are Euclidean tangent cones. That means that we don't end up with the limit where the tangent cones are things like, are just norm spaces, like taxi space. How would we show M infinity is connected? So this is a really important open question. And let me just sort of show what sort of ingredients you might use to try to show the limit is connected. Does it contain geodesics? Now we remember we had those counterexamples that didn't have geodesics, but those examples had min A going to 0. So how would we try to show M infinity is connected? We want to have to use this min A condition in some way to show it's connected. So for Gromov-Hausdorff limit, Gromov proved that the limit spaces are connected and that they're geodesic, they have geodesics between every pair of points. He proved this by showing midpoints converge to midpoints. But for Swift limits, the midpoints could disappear. And what we're saying in this conjecture is that scalar and min A combined will prevent midpoints from disappearing if they're the midpoints of points that don't disappear. So given P and Q that are in M infinity, if there are points in the limit space, we know there are points Pj, Qj, and Mj that converge to P and Q. We understand that notion. And now taking Xj to be the midpoint between Pj and Qj, can we show that midpoint doesn't disappear? Well, we talked about last time that one way to prevent a point from disappearing is to show the filling volume of its ball stays large enough. This should say boundary of the ball is bigger than this. Remember, I talked about this was a technique you could use. If we show the filling volume of the boundary of the ball is big enough, then we could take a limit. The filling volume of the limit of the xj's is going to be big, and then the volume will be bigger and it will be in the set. That would work. Can we show this? We would have to use that xj as a midpoint because other points can disappear. And we have to use that we have the min A condition. And one possible way might not be to use filling volumes of this ball, of this boundary of the ball, because this might be very hard to control and it's unclear how you could ever use the PJs and QJs are converging to control this. But perhaps we could use slice filling volumes where we take our FJs to be distanced to the endpoints. This is kind of like imitating Cheeger holding splitting for Ricci curvature. So if we use FJ's distance to one of the endpoints, perhaps we could use a sliced filling volume instead of a filling volume and get things under control that way. This is open. I am giving you a suggestion of what one might try to prove this. Any questions? So I just want to remind you, remember that we can have sequence of spheres with many, many wells, okay? And if a point is at the tip of the well, so if PJ was at a tip of a well and QJ was at the base of a well, we know that the XJs can disappear. The middle of the well disappears. That's no contradiction. This is allowing us to have those Illman sequences of spheres with many wells. You must use that the PJs and the QJs are both not disappearing, that they both converge to something in order to show that the midpoint doesn't converge. So what would we be using here? If I say that you just try to control this fill vol, I don't see how you would ever use the PJ and QJ that they're converging. This seems to be not tied to them tightly. But if you use a function like this, where it's distance to PJ, and the PJs are converging, now we can study things and say, okay, the boundary of the balls about PJs might have filling volume estimates, and we can possibly use that. Yes, in the chat. That's completely open, but Gromov wants the prism inequality. It's hard to even say how to define these things if you don't have enough properties on the limit space to start saying things like, how do you state the prism inequality on the limit space? How do you state local mass rigidity on the limit space? You kind of need to picture your limit space as actually having geodesics on it, midpoints on it, things of that sort. All right, so this would possibly get the xj's to converge. If you look at this and you focus on the particular ball that goes through the boundary of a ball about pj that goes through xj, this might actually help you complete this process. If anyone's interested in working on this, I'd be happy to work with them. All right, next. All right, so I said connected lane space we're hoping to do, and the outline last page was how maybe you could show it's a connected lane space. It has geodesics between points. And now for the Euclidean tangent cones part. How would we prove the tangent cones are Euclidean? By Ambrosio-Kirchheim theory, we already know that almost every point in the limit space, there's a tangent cone, TPM, which is a normed vector space. That's the limit of balls that are rescaled smaller and smaller. You get a Swift limit, and you get a ball of 0, 1 in this tangent space. If you take capital R times Ri, capital R, you get a ball radius capital R in the tangent space. So there is this tangent space. It's called a tangent cone because it could be cone shaped. It's also to emphasize that this is only a normed vector space, and it is not known to be Euclidean. It is m-dimensional, that's correct, but it's only normed. That's already known. No further work needs to be done to know this much. This is already complete fact. But the conjecture says that they're actually Euclidean. There's an inner product on them, not just a norm. So perhaps we could use geometric stability of a rigidity theorem that implies a ball is a Euclidean ball to try to prove that this guy is actually Euclidean. So remember, there was rigidity theorem, particularly the prism rigidity theorem, that could be used to show, or the mass rigidity, to try to show that the ball is a Euclidean ball. If we show that this tangent space satisfies the qualities of the rigidity theorem that shows it's flat, that would be enough to show that this is a Euclidean ball. So those rigidity theorems that I stated that imply that something is a flat ball or a flat torus or a ball inside it is flat, those could be used to help with this step of getting Euclidean tangent cones. Once you get that this is Euclidean tangent cone, you get a really big piece of information. Your lambda p is 1. And so then your mass measure is 1 times the weight times the Hausdorff measure. This should be Hausdorff, not hyperbolic. That should be a math cal H there. So we would have only the theta to worry about. But the conjecture also at IAS includes that the conjectures that the weight should be 1. All the examples where the weight went up involved tunnels that were increasingly tiny, and we are forbidding ourselves to have such increasingly tiny tunnels. So the conjecture made at IAS is that, in fact, the weight is 1. So if the weight is 1, then now our mass measure exactly is Hausdorff measure of dimension 3. Now we have so much more information. Hausdorff measure of dimension 3. The slices will be Hausdorff measures of dimension 2. Everything will be so much more controlled. We can start talking about those areas. We can start talking about deforming areas. We can start talking about minimal surfaces and how the minimal surfaces areas are the minimum areas of nearby surfaces. We can talk about what it means to be mean convex. If you have all this information, weight theta is 1, Euclidean tangent cones, connected lane space, now we can say prism inequality has this statement. Prism inequality is defined using these kinds of notions. Distances between points, edges of a cube, areas of the outsides, mean convex can be defined. All of these things can be defined using Hausdorff measures instead of just this mass measure. And now it has a better sense of what we mean by scalar greater or equal to 0. All right, but that would require us to prove this. We would need to prove this goes to a Euclidean ball. It goes to a normed ball right now. To prove it goes to a Euclidean ball, we would need to use something that shows things are Euclidean and flat. And that's why I was saying geometric stability theorems or conjectures right now could be applied to try to show these balls are Euclidean balls. Now, this technique is very similar to ideas of Cheeger-Colding. Cheeger-Colding proves splitting theorem. This is a geometrically stable theorem with Ricci curvature bounds. They measure Gromov-Hausdorff limits and get Ricci curvature bounds and splitting on the limit space. They use the splitting on the limit space to control the tangent spaces. They use the splitting and they split and they split and they split and they get some of the tangent spaces are Euclidean because they're using splitting theorem. We wouldn't have a splitting theorem. There is no real splitting theorem for scalar non-negative. There's one that's stated that people could look at, but when I discussed it with Chodosh and Eichmeier, they were not so confident that that sort of splitting theorem would be natural to extend to a limit space. But we do have geometric stability conjectures that would say the ball is Euclidean. So rather than splitting off one direction at a time, we would do everything at once. This is a Euclidean ball because it behaves certain ways. It has certain isoperimetric behaviors. Then its mass would equal 0. It has prisms behaving certain ways. Therefore, it is a Euclidean ball. So that's the approach. So all these different conjectures are interconnected in this way. And when we met at IAS, we really tried to build up these conjectures exactly right to line up with one another so that the whole thing could be solved together. And remember, the precise statements of the conjectures is in that conjectures paper that I provide a link to. That's which just has a list of all these IAS conjectures and explains them. This should be a math cal H3 again. This is an open question that one might want to work on in the first place before doing all this work in between. So I'm saying that one consequence of Euclidean tangent cones being Euclidean is that the mass measure of T infinity is the Hausdorff measure of dimension 3. I'll fix this in the notes. This is a Hausdorff measure. But you could also just try to prove that this is the Hausdorff measure of dimension 3 directly without going through this process. In the Ricci curvature case, this is proven by Colding in his paper that starts with the word volumes, ... okay? Back in the 90s, in the very early 90s, 94 or so. If we could prove the mass measure of the limit space is actually equal to Hausdorff measure of dimension 3, that would be a very important, interesting result that could then be used to help perhaps prove some of these. The only thing I really want to warn people is that knowing that the mass measure is Hausdorff does not in any way imply that the norm space is Euclidean, okay? Lambda equals 1 doesn't go backwards. This is not convertible. If it's Euclidean, lambda is 1. But if lambda is 1, it's not necessarily Euclidean. So we won't be able to go backwards, but it will still be a beautiful theorem to know. And it would still be publishable as having extended Colding's work to the scalar setting. All right, so that's the end of the slides here. I think what I want to do, since we have 4 minutes, is basically take people's questions, but I'm going to go back and bring up the other slides with the examples so we can look at them again from this perspective. But let me ask questions on this slide before I switch. Okay, so I'm going to bring up the images from lesson 2. Full screen mode. Here was the open problems in scalar curvature. And we had a lot of pictures at the beginning. All right, so a picture like this has tiny min A's. You want to keep in mind that would have tiny Minets. I want to go all the way to the conjectures. This would also not be allowed because it would have very thin tunnels, and thin tunnels will make tiny Minets. So this is the example where we had it proved to a space that had no geodesics at all. So these long, thin geodesics are causing a small Minet. If we wanted to try to prove that the limit space is a geodesic space, you would want to say that if you have, say, a point PJ here and a point QJ here, and you found the midpoint XJ, which in this case would be in the tunnel, we want to say that XJ doesn't disappear if we assume scalar and Min lower bounds. But one way to think about it is to look at the sequence and say, okay, if I look at PJ and QJ here, and I take a distance from PJ and I create a slice, what does that slice look like on this bad space? And does that slice make it easy for us to find that tunnel? I mean, sorry, is it easy? Does that slice make us find the minimal surface that's so small? Can we use that slice to show that we have a small minimal surface? You test your steps of your proof on these examples. Okay, this is the main one that gives you the rigidity. This is the prism rigidity. What does it mean to say mean convexity? Area of sigma t greater than or equal to area of sigma 0. This would be a way to define mean convex on a limit space. Areas we're going to try to control using slices. Slices that define boundaries of cubes. How would we use slices that define boundaries of cubes? Probably you want to use level set distances from the face of a cube as opposed to distances from a point. Distances from a face. That would then be the function you would be using to do your slicing. Distance from another face, slice it this way. Distance from the front face, slice it that way. You could maybe slice and slice and slice again. A single slice should be enough for starting to talk about areas and mean convexity. We'd like to be able to say, does mean convex on the sequence imply mean convex in the limit? Dihedral angles is just using volumes. This is very well controlled under volume preserving intrinsic flat convergence, so we don't need extra work to understand the dihedral angles. That's well understood. Is this Hausdorff measure or something complicated involving a lambda? No, we don't know yet. It would be nice if it was Hausdorff measure. The area will need the slicing. So if you want to talk about whether this theorem holds on the arbitrary limit space, you would have to deal with slicing. Here's the widths and unstable minimal surfaces that was used by Marcus and Neves. The width is defined with sweepouts, area. Sweepouts are defined with functions, ft. Maybe you want to look at slices of those functions and understand sweepouts. Yes. Thank you very much. So I think actually time is up. And so I'm going to end now. But you see, I have these all out so we can talk about the questions related to the actual conjectures now that you all know what slices are and everything else. Thank you.
Thank you, Christina. You could continue if you wish. I mean, we have plenty.
Okay. I'll maybe say a tiny bit more. Okay. So for scalar sphere rigidity, does it hold an M infinity with this kind of a sequence? You would use some sort of slicing to define how the width gets to the limit width. And then you would say, okay, how are we going to prove the rigidity on the limit? Well, they proved their theorem with Ricci flow. So that could be tricky, but one way you can do is the same kind of question that Bamler and Burkhard Grimm have studied, is by saying you assume the limit space is a manifold. And then you say, well, if your intrinsic flat limit to a Riemannian manifold and your intrinsic flat sequence has the scalar curvature bounds and the Minet condition, can you assume that the limit space has all these properties? Now what you want to do is say, okay, take the slices back and forth between the two. That process of converting slices from one space to the other, converting sweepouts from one space to the other, is going to involve the intrinsic flat convergence. So that's another thing to keep in mind. And we have these. And here were all the different rigidity theorems. And remember, it would be of interest even if you could just prove volume convergence for any of these, because that's the first step needed to show that a subsequence converges in the volume preserving intrinsic flat sense. Can you get the global volume convergence? That's a purely scalar non-negative question. If you use Ricci flows to help, that would be controlled. People know how volume evolves under Ricci flow. The scalar curvature, people know how scalar curvature evolves under Ricci flow. It is completely open about volume above, distance below, and running Ricci flow from both of them. That would be very interesting to investigate. If one does that, then we'll check if these theorems hold if you assume VADB convergence. Some of them already are known if you assume C0 using the work of Bamler and Burkhardt-Grimm. But if you assume only VADB, can you use those Ricci flow techniques? All right, so these are the non-examples again. Right, here's the IS compactness, which I added more to. And then there was one people, I mentioned before that Park Tian and Wang, they actually proved the IS compactness theorem for this very special case where they had assumed they were warp products. Now that we have the volume above, distance below theorem, which is newer than this original proof, you could try now, could you possibly prove this compactness theorem if you assume VADB convert, you assume the sequence is graphs. So if you try to prove it with graphs, you could try to use the VADB convergence the same way that Cabrera, Pacheco, Perales, and Ketterer proved the torus stability using graphs. Raquel is here, so she's probably not here at the moment, but she will be here next week. So you could discuss that with her if you were interested. Let me just check the chat. I'm going to stop. Thank you very much. And I will leave it now for discussion. Perhaps if no one wants to ask questions with the recording on, we should turn off the recording.
Thank you very much, Christina. Are there questions? I don't see any in the room, and maybe in the chat or.
No, there's no questions in the chat.
No,
So I think people will talk after the recording is off. That's what happened the last 2 times. All right.
Well,
thank you very, very much for the opportunity.
Thank you so much for this series of lectures. Actually, for the other people, we should have had this series last year in Paris, but the situation was not good, and
Yeah.
I'm happy that it happened this year.
Yeah, I'm so happy you all organized this. I really want to thank you so much for organizing the summer school for everybody. Maybe everyone here thanks you together.
Thank you.
Thank you to the organizers so much. I really enjoyed all the lectures I attended. I saw so many exciting results, and
Thanks.
I look forward to next week.
One last word is next week there will be a continuation of this lecture by Raquel Perales. And so if I remember, I have this, yeah, it's on Tuesday at 4 p.m. Paris time. So please come. Everybody should come. Thanks a lot.
Thank you. Thank you so much.
Have a nice afternoon.
You too.